Okay, hello, how are you doing? Now, what I'm going to do is I'm going to give you just continue with the notion of the subspace. Remember, we introduced the vector space. This is a collection of objects that we refer to them as vectors with two operation, addition and scalar multiplication, that behave like, like the usual operation that we have with the addition and scalar multiplications. The addition is going to be commutative, associative. There is an element of the zero. Okay, each vector would have the opposite. So that will cover all the previous examples that we have under this new term of the vector space. We can have a classic one is vector space of the in the Euclidean space. Okay, all the n-dimensional one, or n, or 2, or 3. Then we can have a vector space of continuous function, integrable functions, okay, matrices, n by n matrices. So that's a vector space. So that will help us to prove the theorems in a more general format. Then the vector spaces are too big, so we may considering some sub-collection, subsets of the vector spaces. Those subsets will refer to the subspace if these subspaces by themselves or itself, they are going to be a vector space. So this means the operation that we have for the general vector space, addition and the scalar multiplication, it's going to be also the operation for the subspace. But there is one more condition. The condition is this subspace must be closed under this operation. So this means a subset of a vector space is a subspace if the sum of two vectors, two members of the subspace, is going to be inside the subspace, and if the scalar multiplication, a scalar multiple, if you like, of a vector space in the subspace would end up in the subspace again. So for the other properties, it's already satisfied because it's in the general vector space. So we gave you some example of the vector spaces the other day. Now we are going to continue, introduce new subspaces and work. So in order to recognize the big space, we may pick some special subspaces and investigate the property of the general one. So we end up with some expressions like a linear combination. When we say a vector is a linear combination of some others, means just, v is equal to the 2v1 minus 3v2 plus, okay, 5v3. So it's a linear combination, a scalar multiple. So for example, in R3, you have the ijk. So we are going to continue getting this linear combination would give us some very interesting sets of vectors. We refer to some of them as independent and the dependent, and we need all of them. So what we need eventually is we need a basis for our space. We want to have a group of special vectors that create everything in the general space that we're going to have. So for the next couple of sections, this is what we are going to be heading, okay? So we continue. There is one more definition in section 4.2. I take that one too, then we get to the 4.3, which is very important section. Give us a new concept. They are not difficult, but there are lots of expressions that we have to get to know them in order to be able to get to the more serious theorem for future. Okay, so we are going to continue. There is just one definition left from 4.2. So we finish this one first, 4.2. When we talk about the subspaces. Now we are going to have an expression that we call it a spanning subspace. So, or a spanning a vector space. A spanning a vector space means you may find a group of vectors that can generate any element into in your vector space. Eventually, we are going to define a basis. So let's see what is this expression. We are going to use it quite a lot. So we are going to introduce it here. What is a spanning a vector space, okay, expanding a vector space. And so if you have a group of vectors such that every vector in the given vector space can be a linear combination of this given one, we are going to have a spanning vectors. Okay, so there you are. So this is it. Suppose we have a vector space. Suppose v1, v2 up to the vn are going to be vectors, in a vector space, let's say V. Okay, vector space V. Then we are going to say that these vectors. So these vectors span the vector space V, the vector space V, if each vector in the vector space is a linear combination of these. Okay, if that's going to be definition, every vector space, every vector in the vector space can be expressed as a linear combination, can be expressed, okay, can be expressed as a linear combination. We talk about the linear combination, okay, of this, okay? So of V1, V2 up to the Vn. Okay, so in this case, we say that these vectors span, create, generate, okay, the vector space V. Okay, so if you want an example, the most popular one, if you go into R3 and get the standard vector space, okay, so if V is equal to the R3, three-dimensional, okay, Euclidean space, then the standard, okay, the standard unit vectors, I, J, and K. Okay, these vectors span, okay, span R3. Span R3, you see, because if, you know, if you have, if X, Y, and Z is going to be a vector, in R3, then you know that X, Y, Z can be written as what? X times I, Y times J, plus Z times K. Okay, just remind you that where you see I is 1, 0, 0, J is 0, 1, 0, and K is equal to the 0, 0, and 1. Okay, so IJK is going to be, we call it a spanning set. A spanning set because, you know, we can create that vector space that we're going to have. We are going to be interested in very, very special one. Okay, and so now it's not going to be difficult to, we are going to consider, you see, if a setup vector would be given to V2, any setup vector, V1, V2, up to the Vn would be given to you, we can consider all the possible linear combination okay, all the possible linear combination of this given vector. You see, if you consider all these linear combination, so that give you a vector space. We can write down as a theorem. It's very obvious result that all these spanning, you see, this is very obvious theorem. We write down as a theorem so that we keep it. Okay, so and that's it. If you have a set of n vectors, if v1, v2 up to the vn are going to be our vectors, okay, are vectors in a vector space, vector space, vector space B. If you consider all the linear combination of these vectors, okay, all the possible one, okay, then you have a subspace. So if U is the set of all, okay, all possible linear combinations, all possible linear combinations of these vectors of v1, v2 up to the vn. Okay, so if you pick any vector in the U, that is going to be, that vector is a linear combination of v1, v2 up to the vn. If this is going to be the case, then okay, then U is going to be a subspace. U is going to be a subspace, okay, is going to be a subspace of V, okay, subspace of V is spanned by, okay, by these vectors. The vectors, okay, the vectors V1, V2 up to the Vn. Okay, so this is going to be the case. In this case, we write, in this case, we write, okay, we write U is equal to the span, okay, that's it. U is equal to the span of V1, okay, V1, V2 up to the Vn. Okay, when you write this expression, so quickly that would tell us that any vector, you see, if you want to pick any element in the U, that element in the U is a linear combination of V1, V2 up to the Vn. We call it a spanning subspace. A spanning subspace. It's not difficult to prove. You know that you have to prove that the sum of two vectors in U is going to be in U again. It's easy because each element is just a linear combination. Okay, I can prove it for you, but it's not a big deal. Okay, if you pick two elements, so you know, just the proof is going to be, if you pick two elements, you see, if you pick, let's say U and V are going to be our vectors in U, then it's clear that U plus V, okay, and scalar multiplication alpha U are going to be R in U. Okay, because it's a linear combination. If you add them together, it's a kind of, because the V1, V2 to the Vn are the same. You see that we just show you. If you like to see it, you see this is going to be a situation they're going to have. You see your U is what? Your U is going to be something like a scalar multiplication, a1 v1, a2 v2 up to the an vn. That is u. What is v? Again, a linear combination is going to be something like b1 v1. This is going to be b2 v2 up to the bn vn. If you add them together, so what do you have? If you add them together, you can factor. You see, if you have a u plus v, you get the a1 v1 b1 b1. You can factor out. You see that give you the v1, that give you the v2, and you just keep going. We get to the an plus bn times vn. They are all a scalar multiplication, scalars. So we can rewrite it as u plus v. So this is going to be something like a3 v1. Okay, this, you can call it whatever you like. You see, you can call it alpha 1, or you see, c1, let's say. This is going to be something like c1. This is going to be c2. And you get to the cn vn. You see, if a and the v are a linear combination of v1, v2 to the vn, it's clear that if you add them together, the result also is going to be a linear combination of those vectors. Okay, and so this means u plus v is in u. Similarly, the other one. Just to get the feeling, of what's going on. So that's a notion of the spanning set that we are going to use quite a lot in this course. So we make sure that you understand it, what we are talking about. And we have a couple of famous examples that you have to know it. And when you see it, you see, for example, we already talked about it, that R3, the three-dimensional space, it can be a span. So it's a span by I, J, and K. So this means every element in R3 and any vector in R3 is going to be a linear combination of ijk. Okay, and in general, if you have Rn, n-dimensional, that can be a span. Right, this set is going to be A1, E2, up to the En. They are going to be like ijk. You see, it's where you get to know these. We are going to use them. Okay, this is going to be where E1, 1 is in the first position. Okay, E2, 1 is in the second position. And you just continue. We get to the En. In this case, 1 is going to be in the last coordinate, if you like. Okay, these are a special case in R3. 1, 0, 0, 0, 1. Okay, 0 and the 0, 0, 1. So get to know them. These are going to be eventually, we call them a basis. Okay, that's a 1, 2. And this, the third one, is also very popular. Remember, we talk about the vector space of a polynomials. We emphasize that a vector space of a polynomial of degree at most n, at most 2, at most 3 is a vector space. I give you example the other night that you cannot say that the polynomials of degree exactly 2, exactly 3. You must say okay, we refer to it at most, and this is going to be the spanning set. These vector space would be denoted by Pn. Okay, so the Pn is, get to know it, is the vector space, okay, is vector space, is the vector space, the vector space of all polynomials, of all polynomials of degrees, degrees at most n. At most n means the degree is n or less. At most 2 means the degree can be 0, 1, 2. At most n means the degree can be 0, 1, 2, 3 up to the n. If this is going to be the case, you must know that in this case, note that. Remember the definition of a polynomial. A polynomial is a combination of terms, combination of powers of x. So simply this means this vector space, Pn, can be a span. A span by what? A span by the power of the x. The first power is x to the 0 is going to be 1, x squared, x squared up to the x to the n. You know that any polynomial is a combination of these. If you have a quadratic polynomial, what's the formula for the quadratic polynomial? It's going to be p of x equal to the a plus bx plus cx squared, if you like. So 1x squared to the xn is going to be the spanning set for the Pn. We are going to use this from time to time, and we're going to repeat it over and over. So get to know them. So that's if you see this notation, we call it a spanning subspace. A spanning subspace means every element in the vector space can be written as a linear combination of these terms. Now you have some examples, some problems in your book that they give you some sets and they want to check whether this is going to be the case. It's like the linear combination that we did. So I just give you quickly one of them so that you know what's going on with these expressions. So you may see these type of problems. You may be asked to determine for the spanning sets. You may ask to determine whether determine whether the vector 3, comma, -1 and 11 lies in in the subspace subspace that is going to be, this is a subspace. They give you a span of -1, 5, 3, and this is going to be 2, comma, -3, 4 of R3. So you know the meaning. This subspace means any vector is going to be a linear combination of these two. So if you want to find out whether your vector 3, -1 and 11 is in this set, you must show that this vector can be written as a linear combination of these other two. So that's a meaning. Solution. So check. So we're going to check to see if this is going to be the case. We may call this one U. Just want to repeat it. So I just remind you that this vector 3, -1 and 11 is in U if it's a linear combination. If you can find if there are some scalar, there are some scalar like C1 and C2 such that your vector, which is a 3, comma, -1 and 11 is what? It's going to be C1 times -1, 5, 3 plus C2 2, -3, and 4. Okay, so if you can find this C1 and the C2, the answer is yes. If you cannot find it, the answer would be no. Okay, the way we do it, we did it the other night. You just get this combination, you multiply the C1, C2 inside, then you add them together, and you let the terms to be equal to each other, the coordinates, and then a system of the equation, and we take care of it. Okay, so this is going to be the result. This is going to be 3, -1, 11, equal to, get this combination, you see, the first component, -C1 and the 2C2, -C1 plus 2C2. The second part is the 5C1, 5C1 minus 3C2. And the last part is 3C1 plus 4C2. Okay. So you are going to let the corresponding component to be equal to each other. You see, this would be equal to 3. This would be equal to the -1. And the last one into the, okay, equal to the +11. You solve that system of the equation. If you get an answer, you see, in this case, that's it. You must get some non-zero numbers. Otherwise, the answer would be no. So I'm going to let them to be equal to each other and to take this one down. Okay. So we're going to do quite a lot of this type of ideas. So this is going to be a situation we're going to have. If you let them to components to be equal to each other. So the first component was a -C1, -C1 plus 2C2. And for the vector, we have 3. Okay, this is it. See, this is 2. That is the 3 here, and the -C1 plus 2C2. I do the same thing for the other one. Okay, so the next one is going to be 5C1. It's a 5C1 minus 3C2. 3C2 equal to the -1. And the last one is 3C1 plus 4C2. You want it to be equal to, okay, equal to the 11. As you can see, you have a system of 3 equations, but 2 variables. So the way we do it is you can use those matrix form, but it's going to be easier to just solve it right away. So what you do is you consider 2 of these equations, you solve for the C1 and the C2, then check the numbers here. If your results satisfy here, then you have a solution. Okay, so I'm not going to change it to the matrix form, so I just pick these 2 and quickly solve it. So I have a -C1 plus 2C2 equal to 3, and this is going to be the 5C1 minus 3C2 equal to the -1. Okay, so what I do is I just multiply the first one by 5, then I eliminate the C1. Okay, so this is going to be the case. So that gives me -5C1 plus 10C2 is equal to the 15. And the next one, I have the 5C1 minus 3C2 equal to the -1. I add them together. Okay, the C's would disappear. So that gives me 7. Okay, that gives me 7C2 equal to the 14. So the C2 is equal to 2. Okay, so we have a C2 equal to 2. Then I substitute it into the other one, to the first one, to get my C1. Okay, so the C2 is equal to 2. So I substitute in the first one, so -C1 plus, okay, and that's it, -C1 plus 4 equal to 3. So the -C1 is equal to the -1. So the C1 is equal to 1. Okay, so I have a C1 equal to 1 and the C2 equal to 2. But you have to check it into the third one to make sure that this is going to be correct. Okay, you check it here, otherwise it's not going to be a solution. So we check into this one. So check the third one. It's going to be 3 times 1 plus 4 times 2 to be equal to the 11. Yes, this is correct. Okay, so the C1 If it's not, you are not going to have a solution. So this is going to be true, and I did it. So the answer would be yes. Okay, so therefore the vector 3, -1, 3, -1, and 11 is okay, is in U, if you like, is in U. So this means that's it. It's a 3, -1, and 11 is a linear combination. We get the first vector, which was a -1, 5, and 3, plus 2 times the other one, 2, -3, 2, -3, and 4. So the answer is going to be yes. Okay, you have quite a lot of these in your assignment, and we are going to do this type of operation, quite a lot, just not bad, just to get some examples, to get to know them. Okay, so this is the subspace, the question in R3. Let's give you one with the polynomials to know how we are going to work with the polynomials. We're going to have 3 sets of examples from now on. Euclidean one, R2, R3, polynomial one, and the matrices. So you will see them when I post your, over the weekend, I post your next, the practice quiz. You know that you are going to have your next quiz, and the quiz is going to be like the one that we did before. I post the solution, then you bring the, I post the questions, and you bring the answer, you submit it on the canvas. But you will see quite a lot of these type of operations. Okay, so I'll give you one with the polynomials to see how you handle these problems. This is it. Suppose f of x is equal to the 2x squared minus 5. Okay, and we have a g of x. G of x is equal to the x plus 1. Okay, they are polynomials. So what do you want to do? We want to show that another polynomials, the function, okay, the function h of x equal to 4x squared plus the 3x minus 7, again is lies in the subspace, spanning space, lies in the, okay, in the spanning subspace, in the subspace span of f and g. A span of f and g is all linear combination of f and g, remember? Okay, so what you have to do, the same thing. So you have to find some scalars to see if you can write h as a combination of f and g. Sometimes it's easy to look and find out, but we want to get the operation just to show you how we're going to handle these type of problems. Okay, so the solution is going to be, again, you are going to find the scalars. So you'd like to find scalars C1 and C2, okay, such that H is going to be a linear combination. You see H is going to be equal to the C1 F plus C2 G. Okay, it's going to be in the spanning set. It's going to be linear combination. So substitute, simplify. That's it. Your H is what? H is 4x squared plus 3x minus 7 is equal to the C1 times F, which is a 2x squared minus 5. Okay, 2x squared minus 5. And this is going to be the C2, which is x plus 1. You have to multiply it for the polynomials. We use the fact that 2 polynomials are the same if the coefficients of their corresponding monomials are going to be the same. So this means you let the coefficient of the x squared from one side to the other side to be equal to each other. coefficient of x, and the coefficient of the constant. That gives you the system of the equation that you are going to be interested in, okay? So let's organize it or simplify it. So multiply, so that give you 2c1x squared minus 5c1, and that give you c2x plus c2. Okay, order it as a polynomial, starting with the highest exponent if you like. So this is it. I have the 4x squared plus the 3x minus 7 here. So on the other side, I have the x squared, c2c1 x squared. Then put the x, it's going to be c2x, and the constant. The constant would be c2 minus 5c1, like in calculus. Okay, so the coefficient of the x squared must be equal to each other. Okay, and then the others, coefficient of the x equal to each other. Okay, and eventually the constant term. So this is the way you form that system of the equation. Okay, and so this is it. We can do it right here. So what I have is, from the first one, that give me 4 equal to the 2c1. So 2c1 equal to 4. Okay, from the second one, I get the c2 equal to 3. c2 equal to 3. And from the last one, I get the c2 minus 5c1. 5c1 must be equal to the negative 7. You see? That's why we do it. So from the first one, you get the c1. Okay, so that gives you the c1 is equal to 2. And from the second one, c2 is equal to 3. And you check it here, you see that it is going to be 3 minus 10, which is a negative 7. Okay, if you put it here, you have to check. It's going to be 3 minus 10 equal to the negative 7. So this is going to be a solution, and then we're done. And that's it. The answer is yes. And the h was 4x squared plus 3x minus 7 is equal to the c1, 2. 2 times 2x squared minus 5. And the c2 is going to be 3. 3 times x plus 1. So h is going to be a linear combination of these other two. Okay, get to know them. This is the way we operate quite a lot from now on. You get to know a spanning set. So spanning means just a linear combination of these vectors. If this is big enough, if it's going to be big enough, we'll create the vector space, and that is what we are looking for. We are looking for a good one, and we are going to find one. Okay, so that was the leftover. Oh, I should give another one. This one would be useful for future. Okay, this question is going to be used quite a lot. So what's going to be the next one? The next one is a suggestion for R3. You see, we already talked about the spanning set. IJK span the R3, but this is not the only set. You may have some others. And this question is going to be used in different formats, several places in future. So let's do it. We just want to see them now. Then when we see it again, so we have some idea of what's going on. Okay, so what is this question? You want to determine if this is true. Determine. Okay, that's it. We want to determine whether R3 can be a span. R3 is going to be a span. Okay, a span of these three vectors, V1, V2, and V3, where these vectors are given to you as follows. the vector v1 is equal to 1, 1, 2. The vector v2 is equal to 1, 0, 1. And the vector v3 is equal to 2, 1, 3. You see, that's the one. So you want to do it in general, not like the other one that we did. The other one, what we did, a specific vector was given to you, and then you check if it is going to be in a spanning subspace. In this case, you have to prove that any arbitrary vectors, okay, any, not the special one. Any vector is in R3, any vector is in R3 is or can be written as a linear combination of these three. So you have to pick one arbitrary vector, okay? So this is what we are going to do. Solution. No restriction, just pick one. So that's it. You give me one, I check it for you. So, okay, suppose this is the vector in question. Suppose B equal to B1, B2, B3. Is a vector in R3. In R3. If you can find a scalar C1, C2, C3 such that this B is a linear combination of V1, V2, and V3. CV1, C2, V2, C3, V2. In that case, we can say that they span the whole subspace. Okay, so you have to find, okay, so this is it. We should find or find if you like. So that's the question. Find, okay, find scalars, C1 numbers, C2 and C3 such that your B is C1 V1, C2 V2 plus C3 V3. If you can show that these C1, C2, and C3 are possible or exist, in that case, the answer is yes. Okay, and we did it for any vectors. So as usual, form this combination, result with the system of the equation, and we check to see if that system would have a solution, okay? So what's the B? B is B1 as a vector, B2 and B3. That's your B. Equal to what? C1. C1 times V1. What is the V1? 1. 1, 2. Plus C2 times V2. 1, 0, 1. Plus C3 times the V3. 2, 1, 3. There's some method in future that we make it shorter, but the idea is the same. Okay, as usual, multiply inside, make it those combination that we talked about it already. So it's going to be equal to the first component, C1, C2, and the plus 2C3. That's the first one, comma. Second component, C1. Okay, C1, that would be 0. So we get a C3, C3. The last one, 2C1, 2C1 and C2 plus 3C3, 3C3. That's going to be the last one. Okay? Let them to be equal to each other. So what's going to be the system that we have to solve? So you have to check this one, that C1 plus C2 plus C2C3, you want it to be equal to the B1. The next one, C1 plus C3, you want it to be equal to the B2. Okay, B2 and what else? It's a 2C1. 2C1 plus C2 plus 3C3. You want it to be equal to the B3. You see, you have to check as a system of the equation and you solve that, this system would have, this system would have a solution. That is going to be the idea. So we just go for the matrix. See, if you change it to the matrix form, what is going to be the result? So the matrix form is this one. Remember the coefficients, we have a 1, 1, 2, and that's a constant term. If you go with the augmented matrix, and this is going to be 1, 0, 1, the B2, and this is going to be what? It's going to be 2, 1, 3, and the B3. That's going to be, the format of the augmented matrix. You can stay with this one and check to see if there is any solution, okay, at the end, or you can change it to the matrix equation. You see, if you call this one A, this is going to be the case, okay, and you know that it's going to be eventually something like, okay, AX equal to the B. And we already talked about it. This would have a solution if this A is going to be invertible. Okay, so you know that you are going to have the X is equal to the A inverse B, if you like, if A is invertible, or if the determinant of A is not equal to 0. So it's quick to check if this determinant, okay, that's one way to do it. You can form you go on augmented matrix, and eventually you get the fact that you won't get any solution. Okay, so what I do is I just check the determinant of this matrix. So that's going to be 1, 1, 2, and that's a 1, 0, 1, and the 2, 1, 3. Okay, check the determinant of this matrix. Determinant of A would be 1 times, okay, that's going to be 0 minus 1. I get the negative 1 times, okay, that give me a 3 minus 2. 3 minus 2, and the last one is going to be 2 times. Okay, I get the 2 times, it's going to be 1 minus 0. So if you check what is going to be the result, that give you a negative 1, and this is going to be a negative 1, and that would be a positive 2, which is equal to the 0. So this means the determinant of the A is equal to the 0, and A is not invertible. Okay, you know that if it's not going to be invertible, the system has no solution. Okay, so A is not invertible or non-invertible, not invertible, invertible, and the system has no solution. The system has no solution. So this means it's not possible. Okay, it's not possible to get it. Therefore, no. Therefore, that R3 cannot be created, cannot be a span. Okay, cannot be a span by these vectors, V1, V2, and V3. Very, very important result, and the method that you are going to use for future, because you don't have you see, your vector must be an arbitrary vectors, B1, B2, B3, so you don't have it. So that's, you have to go on with no restriction, You should prove that there is a solution for your system. This technique is very important and very good, and we are going to use it quite a lot from now on to get these numbers. Okay, so if you stay with the augmented matrix, and if you go with the echelon form, you need some condition at the end. Remember, we give you these type of problems to check whether we get one solution, no solution, or infinitely many solution. But this method is much easier. So get to know this method. It's going to be very useful. From now on, we are going to do it. You see, we are not interested in the solution. We just want to see the possibility. That's why this method is good. Okay, in the other problems, you were looking for a solution because you want to write it down as a linear combination. But since it's arbitrary one, and this is not going to be the case, and this type of method is very, very useful. Okay, so get to know this method, and from time to time, we are going to use it. Okay, so there are some spanning sets for the R3, IJK, span it, and sometimes you may get some other vectors that do the same job, but you have to try it. That was given to us, okay? So we just pick an arbitrary vector in R3 and check to see if you can write it down as a linear combination. So when you write it down, you have to solve this system of the equation. So if you change it to the matrix form, you know that the system would have a solution if A is invertible. A is the matrix of the coefficients. We check the determinant, it's 0. So it's not invertible. So this means you cannot find the solution. And R3 is not going to be, okay, it cannot be spanned by those vectors. So these are some examples that will help you to go through the problems that we have. Now, that was 4.2, very dense section, okay? But that will help you quite a lot to get to the 4.3. What's the 4.3? You see, what was the situation over here? We talk about the spanning set. So it's very good, it's interesting, helpful to be able to generate your vector space, which is a very big one, generated by some of these spanning subset. If you have the spanning subset, that would be very good for you. We are going to find, okay, we are going to determine how we can find those spanning subspaces, okay? So that's the idea of 4.3, okay, 4.3. We're going to use, we are going to bring new, okay, new expressions, if you like. That spanning subspace that we're going to create at the end, we call it a basis for a basis for the vector space. But we have some very interesting concept that we're going to see here, okay? So it's a 4.3. Again, dense section, lots of problems, but not bad. Prepare us for the section 4.4, which is a very good one. Okay, there are some expressions that we're going to define. We already talked about the spanning, okay, subspace or the spanning set of vectors. We are going to consider a set of vectors that introduce two notions. The notion of a linear independent and the linear dependent. Okay, both of them are going to be related to the linear combination that we talk about it. You see, if a set of vectors is going to be linear dependent, means some of them can be written as a linear combination of the others. But if they are linearly independent, this means it's not possible to write one of the vectors as a linear combination of the other ones. Okay, so that's basically the definition. But before we change it to the format of a algebraic form, and the set of vectors would be given to you, then you are going to investigate it for us. Okay, that's the idea of this section. So getting the definitions as is in your book and some examples. So what is going to be these terms that we talk about it? The title is, I think, is a linear, okay, linear independence. That is a title of this section, probably. But we are going to talk about those two ideas that I talk about it. Now, I'm going to define a linear dependent and independent. This is it, the set of vectors. The definition seems to be different, but at the end would be the same thing that I talked about it. The set of vectors. Set of vectors, this is it. V1, V2 up to the Vn. Okay, in a vector space. In a vector space. Okay, vector space V is said to be linearly dependent. Okay, linearly dependent This means, a vector can be written as a linear combination of the others, but they define it somewhere somehow different, but it's the same thing. Dependent if there exists okay, scalars, okay, C1, C2 up to the Cn, not all equal to the zero. At least one of them must be a non-zero, because you want to write the vector in terms of the others. Okay, if there exists a scalar C1, C2 to the Cn, not all zero, okay, not all zero, such that C1 V1 plus C2 V2 up to the Cn Vn is equal to the zero. That's it. You see, not all zero. If one of these is going to be non-zero, you can solve for that one. For example, if C1 is not equal to the zero, you know that. You can solve for V1. You move everything else to the other side, you divide by C1. So V1 is a linear combination of the others. If C5 is not equal to the zero, you can move everything to the other side except C5, V5. Then the V5 is a linear combination of the others. So they are linearly dependent if, if some of these vectors can be written, or at least one, as a linear combination of the other ones. This is algebra. This means if you try this one, you try the C1C V2 to the Cn Vn equal to the zero. And if you solve this system, it's going to be a system of the equation. If you solve this system, and at least one of these C1, C2 to the Cn is a non-zero element, then it's going to be dependent. Otherwise, if all of them happen to be zero, the system is dependent. Okay, so again, introduce the other one. If it's not going to be possible, then it's a dependent. The set of vectors, okay, the vectors that we talk about it, is going to be linearly independent. Okay, linearly independent is going to be if anytime you have the C1 V1 plus C2 V2 up to the Cn Vn is happen to be equal to the zero, then all these C1 C2 to the Cn must be zero. Okay, can only be satisfied, when all the C1 C2 up to the Cn are going to be equal to the zero. That's it. Because if all of them are zero, you cannot write one of them as a linear combination of the other one. That's it. So we form this identity. We let it equal to the zero. We solve the system. If you get only trivial solutions, C1 equal to the C2 to the Cn equal to the zero, the vectors are linearly independent. But if you solve it and you get at least one of these numbers going to be a non-zero number, in that case, they are linearly dependent. Okay, so that's going to be linearly dependent or independent one. Okay, so your job, as usual, we give you one and we ask you to check. We give you 4 examples on the test. Okay, one with the vectors, one with the matrices, and one with the polynomials. Be ready for it, and you will see all of them in your next practice quiz. Okay, so check the first one. The first one is you want the vector type. You want to determine? It's going to be easy, but be patient to get the correct answer. So determine whether the set, this is it, the set of vectors are going to be 1, 2, 0, 0, 1, negative 1, and the 1, 1, 2. Determine if this set is linearly independent. Is linearly independent. Independent in R3. That's it. Okay. Solution, this is the way you check. You form that identity and then you solve the system. Okay, so you're going to suppose, that's the way you do it. Suppose C1, okay, 1, 2, 0 plus C2, 0, 1, negative 1 plus C3, 1, 1, 2 is equal to the 0. Okay, it's a vector, if you like, the vector 0, which is 0, 0, 0. Okay, because you use the vector form for the other. Okay, just put them together, the first component, and just get the system of the equation. So what's going to be the first one? It's a C1. This is 0 plus C3. The next one is 2C1. When we go on, there are some other method to do it, but not for the time being. Okay, 2C1 and the C2 and the C3. And the last one is 0. This is going to be negative C2 plus 2C3. And you want it to be 0, 0, 0. Okay, form the system of the equation. So what do you have? C1 plus C3 is equal to the 0. 2C1 plus C2 plus C3 is equal to the 0. And the negative C2, okay, negative C2 plus 2C3 is also equal to the 0. You see, you have to solve this system of the equation. It's easily seen, that you can quickly solve it. You don't need any other methods, and that the C1, C2, and C3 are going to be equal to the, are equal to the 0. And, you pick those two of this system and you solve it, okay? So I just give you the result that the C1 is equal to the C2 is equal to the C3 is equal to the 0. You can use elimination method if you like, as is. For example, if you add these two together, you see, if you add these two together, these two would cancel out. So that give you 2C1 plus 3C3 equal to the 0. And over here, you have a C1 plus a C3 equal to the 0, you see? And it's clear. You multiply this one by -2, and quickly we get the fact that, you see, quickly you get the fact that they all is going to be 0. So it's a 2C1, or just for the matrix. It's going to be 2C1 minus 2C3 equal to the 0. So these two would cancel out. That give you C3 equal to the 0, and eventually C1 equal to the 0, and C2 equal to the 0. Okay, so that's it. So they are all 0, means this linear combination is not possible unless all of them are 0. Okay, so the answer would be yes, the vectors are going to be, okay, the vectors are independent, are linearly independent to get these numbers done. Okay, this is one method. There are different methods to check this one. The other method is that if you just get the coefficient of this, okay, the coefficient matrix, the matrix of the coefficients, okay, that is a method one, okay. It's very quick, you can answer it right away really, but this method also is going to be useful. So we call it the method two. The method two is consider the matrix of the coefficient of the system. Okay, consider the coefficient matrix, the coefficient, okay, coefficient matrix. The coefficient matrix would be this one, A equal to, okay, it's going to be 1, 0, 1, 2, 1, 1, and this is going to be 0, negative 1, 2. Okay, so this is a situation that we're going to have. These are going to be coefficient of the matrix. See? The first one is 1, 0, 1, 2, 1, 1, 0, negative 1, and 2. Again, the same idea that we talk about it. Remember, in this case, the matrix form is going to be what? Is going to be AX equal to the 0. Because on the other side is 0. So if A is going to be invertible, remember your X would be what? Your X would be A inverse times 0, which is equal to the 0. So check the determinant of this matrix right away. Determinant of the matrix. Okay, it's easy. That's it. It's going to be 2 plus 1. And this part is 0. And the plus 1 times negative 2. Okay, so that gives you 2. Okay, this is it. So that gives you 2. Just make sure you get it right here. So I have a 2 plus 1. Okay, and that's 1 minus negative 2. Sorry, that's a 3. So that gives you 3 minus 2, which is 1. Is not equal to the 0. So A is invertible and X would be 0. A is invertible. Okay, A invertible, and so that's it. C1 is equal to the C2, equal to the C3, equal to the 0. And there, okay, even you don't need it. If A is going to be invertible, the only solution is 0. So this means the vectors. Okay, so the vectors are going to be independent. Okay, so it's very, very good method to know. You must know all the methods, all the possible methods that we're going to have. So if this determinant is going to be a non-zero number, okay, it's going to be non-zero, then your system, your vectors are going to be linear independent. And it's a very good option, and to know it. Okay, so this is going to be one example. I should give you one with the polynomials, okay? As I told you, we need this type of example to get to know them. So the next example is going to be a polynomial type. And we want to show that. In this case, they ask you to show. And you have in your book, similar problem. You want to show that the set, okay, the set of these polynomials. You have x squared plus 1, comma, 3x minus 1, comma, negative 4x plus 1. 4x plus 1. You want to show that this is going to be is linearly independent. Is linearly, okay, independent in, okay, in P2. Remember P2, polynomials of at most, okay, polynomials of at most, okay, at most, okay, of degree 2. Degree 2. So this means the degree can be 0, 1, or 2. Okay, you want to prove that you just think as them as a 3 vectors. So form that linear combination and to check to see if it's going to be the case. So the solution, get those scalars. Suppose C1 times x squared plus 1, the first vector, plus C2 times 3x minus 1, and the C3 times the negative 4x plus 1 is equal to the 0, 0, 0. Okay, that's it. In this case, it's going to be just, they are polynomials. So it's going to be 0 polynomial. Okay, put them together. Distributed C1 x squared plus C1, 3 is C2x minus C2 minus 4 C3x plus C3. And this is going to be a 0 polynomial. Write it down in the standard form. So the C1 x squared, get the x's. Okay, you have to factor out the x. So it's going to be plus 3C2. 3C2 minus 4C3 is equal to the x. And then you have a negative C2 plus C3. Okay, it's going to be 0. You see, you want to have a polynomial. So it's going to be 0 polynomial, 0x squared plus 0x plus 0. Because you want to let the coefficients of corresponding monomials to be equal to each other. Okay, so we started the x squared, and then we just keep going. Okay, so this is going to be the case. So what's going to be the system of the equation? So it's easily seen that the C1 is equal to the 0, coefficient of the x squared. Then the coefficient of the x, we have a 3C2, 3C2 minus 4C3 equal to the 0. And the last one is a negative C2 plus C3 is equal to the 0. Okay, it's easily seen that from the first one, you already, okay, from the first one, you already got the C1 equal to the 0, and from the other one, quickly, we get the C2 and the C3 are all 0, okay? So the C1 equal to the C2 is equal to the C3 equal to the 0. So the answer is yes. The vectors are going to be, okay, the vectors are linearly independent. And with that. Okay, so this is the example for the polynomial type to get these numbers. Okay, so let's check one with the matrices to make sure that you understand how we're going to apply for the matrices one. Okay, so that's it. I told you 3 examples from now on. Vectors, okay, Euclidean space, R3, R2, Rn. Okay, the polynomials and the matrices. Let's see how we're going to operate with the matrices. So this is going to be our next example. This is it. We want to determine okay, determine whether the set of vectors that we're going to give you in you see M 2 by 2. This means the vector space of all 2 by 2 matrices. Okay, n by n means the set of n by n matrices. Okay, we want to determine whether the given vectors that we're going to give you is going to be linearly independent, Okay, this is it. And this is the set of vectors. They give you, they call it S. And these are going to be 2 by 2 matrices, 2, 1, 0, 1. This is 1. The other one is going to be, and that's a 3, 0, 3, 0, 2, 1. And the other one is going to be 1, 0, 2, 0. That's it. So we want to show that these are going to be checked to see if they are linearly dependent or independent. The same thing. You see your vector, you can call them v1, v2, v3, or just go ahead to get these numbers. So what is going to be the solution? Again, check. You are going to suppose, as usual, C1, C2 are scalars. So we have the C1 times the first one, 2, 1, 0, 1. Okay, plus C2 times 3, 0, 2, 1. And plus the C3, which is going to be 1, 0, and 2, 0. And this is going to be 0 vector. 0 vector in this case is going to be 0 matrix. Okay. So multiply them together and let those terms to be equal. Okay, so this is going to be the conclusion. You see the first component. So this is going to be 2C1 plus 3C2 and the C3. You know that you multiply by all the entries, then I just add them together at the same time. So the next one, C1. Okay, over here that would be 0 and that would be 0. So we get the C1 only. This one, this is 0. We get the 2C1, 2C2, 2CT, 2C3. Okay, 2C3. And the last one, you get the C1, C1 plus C2, and that's it. And you want it to be equal to the 0, 0, 0, 0. Now you know that two matrices are going to be the same if their entries are going to be there. Okay, equal to each other. So that's it. So this is what you are going to get. From the first one, we get the 2C1 plus 3C2 plus C3 equal to the 0. Okay, then you get a C1 equal to the 0. And over here, we get the 2C2 plus 2C3 equal to the 0. And the last one, we get 2C2 plus 2C3 equal to the 0. See, you need 3 unknown, you have 4 equation. It's not a big deal. Quickly, you can see that. You see this is C1 is equal to the 0. And quickly, we can see the other one are going to be all 0 really. You eliminate the C2, then the C3 would be 0. So the C2 is equal to the 0 and C3 is also 0. Okay, so they are going to be not a difficult one. So the vectors are going to be independent. Okay, it's going to be independent, and you are done. There is one group. Okay, so what we did so far, all of them were Okay, the answer was all independent. Let's say get one that it's going to be otherwise. Okay, so because I should give you one that is not going to be satisfied. They all seems to be okay. Nice. So this is going to be a polynomial type again in P2 that we can reject it right away. Okay, already. Let's go to the other side. So I give you this one, which is going to be, they must be dependent so that you get one. Okay, so what do you want? We want to determine whether the set, whether the set of vectors in P2, you know that polynomials of degree at most 2 is going to be linearly independent or dependent. Okay, independent or dependent. Okay, so that's a question. What is the set of vectors? This is the set of vectors. You have 1 plus x minus 2x squared. This is 1. And the other one is 2 plus 5x minus x squared. And the last one is going to be x plus x squared. Check this one. 3 vectors in P2 form that a scalar linear combination solution. Okay, so let's have what is going to be, you are going to suppose C1 times the first one, 1 plus x minus 2x squared. Okay, plus C2, 2 plus 5x minus x squared. Okay, plus C3, x plus x squared equal to the 0. Okay, this is going to be the case. Put them together nicely, just, simplify. So I'm going to multiply and just write it down as a polynomial. So this is going to be the C1 plus C1x minus 2C1x squared. The next one is going to be 2C2, 5C2x minus C2x squared. You can collect the, the coefficients as is, we don't mind. I just wanted to see it. Okay, so this is going to be 0 polynomials. So put the nice one together. Squares is a negative 2C1 and minus C2. And we get the C3. This is the coefficient of x squared. Okay, get the x's plus, we have the C1 here, C1, 5C2, and the C3, that's the x. And the constant is going to be C1 plus 2C2, 2C2, that's it. C1 plus 2C2, and this is going to be equal to the, okay, as usual, 0x squared plus 0x plus 0. You don't have to write, just explain it. Okay, let the coefficient of the corresponding monomials to be equal to each other to see what type of system of the equation we are going to have. So that's it. So we are going to have, this is it, negative 2C1 minus C2 plus C3 equal to the 0. In the second part, we get the C1 plus 5C2 plus C3 equal to the 0. In the last one, we get the C1 plus 2C2 equal to the 0. See, that is going to be the case. And it's not clear like the one that we did before. So you have the two choices to find the C1, C2, C3. You can go with the augmented matrix if you like. You see, if you go with the augmented one, you get the -2. Then we get the -1 and 1. And this is going to be 1, 5, 1. And this is going to be 1, 2, 0. Okay, and of course you have a 0, 0, 0 here. Okay, that would be the augmented matrix. Sometimes you may be interested in the actual solution. Then you go. Okay, so if you want to stay with this one, you can do a little bit of those operations, you know it. So this is going to be R2. I'll give you another method in a minute, but I wanted to see it. So what we are going to do is, where is the -2 comes from? Yes, that's a -2, 1, 2, 0. Yes, you can switch one of them, to get one of them on the top if you like. So I'm going to switch, let's say R1 and R3. I switch this one. Okay, to get one of them on the top. And then at the same time, I can do something here. So it's R2 is going to be R2 minus, okay, minus 2R1. Okay, maybe that's the case. I have the final answer, but I want to do it. So it's going to be 1, 2, 0, 0. Okay, and in this case is R2 minus, so that gives you 0. Okay, R2 minus 2R1. No, I made a mistake over here. So I take this one back and I do the, let's switch it first. So that's 2, 0. Then I have the 1, this is 5, 1, 0. Okay, and the last one is going to be -2, -1, 1, and 0. Okay, so now I quickly change this. It's going to be R2, which is going to be R2 minus R1, and this is going to be R3. So I change it to the R3 plus 2R1. Quickly we get somewhere. So that gives you 1, 2, 0. Okay, 1, 2, 0, 0. And then this would be 0. Okay, that's R2 minus R1. So that's a 3. And this is going to be just 1, 0. And this last one, R3 to R1. So that make it to the 0. Okay, 2R1 is going to be 3. Okay, and that would be 1 and 0. As you can see, quickly, you can change this one into the R3 minus R2. So we get the fact that it's going to be 1, 2, 0, 0. And this is a 0, 3, 1, 0. And now we get the 0, 0, 0, 0. You see? So this means this system would have infinitely many solutions. So it's not the case that the C1 equal to the C2 equal to the C3 would be 0. Okay, in fact, we can find them. Okay, just so the system, so the system has infinitely many solutions. The system has infinitely many solutions. Infinitely many solutions. Many solutions, and the vectors are dependent. And the vectors, okay, the vectors are going to be dependent. Because for independent, you must get only one solution. For example, you can pick C1 equal to the, okay, one of them optional, C1 equal to 2, okay, C2 equal to the -1, and the C3 equal to the, okay, equal to 3. That give you, okay, that give you the fact that you're going to have. Okay, so this is going to be, okay, one method to do it. Again, the other method is also available that we talk about it. If you check the determinant of the coefficient matrix here, the determinant would be 0. So if the determinant would be 0, this system would have, okay, not only trivial solution, if you like. We have some other solution because if the determinant is going to, if A is going to be invertible, you have only one solution, 0, 0, 0. If A is not invertible, this means there are some other solutions. So if there are going to be some other solutions, then okay, then the system is going to be dependent. So you may check it to show that this is going to be, if you get that determinant of a matrix, so I just write it on method 2, you can check it. Method 2 is going to be the determinant of a coefficient matrix, okay? So the one that we did have over here, you see, if you take the A to be equal to the 1, 2, 0, and this is 1, 5, 1, and this is a -2, -1, and 1. You see, if this is going to be the case, we can get the determinant quickly. In fact, you can check it. I haven't checked it, but we can check that the determinant of A would be what? On the first line is going to be 1. So it's a kind of a 5 plus 1. Then it's going to be -2 times, okay, it's going to be 1. And this is going to be a +2. Okay, so that's give you exactly 6 minus 6, which is equal to the 0. So the determinant of A, this is very quick method, I told you before. If the determinant is not equal to the 0, they are going to be independent. If it is equal to the 0, so the vectors are going to be dependent. So I like you to see both methods, to see, you know, to get to know them. Okay, so this is also useful to know. So get these examples and then we continue. That would be enough. We are not done with this section 4.3. I just give you some practical one. There are a couple of theorems that makes things easier for us to be able to do it, but the practical part is these examples. So quickly check some of the problems in 4.2, 4.3, and your practice quiz that I will post over the weekend. So you can start working with some of those examples from both of them, okay? So I will post another one for you by, you know, by Sunday, let's say, to finish this section and the beginning of the next one. These sections are dense, not difficult, it's all dense, are quite a lot. Okay, so that's it. Check your test, you know, just over this weekend, and then we come back and we continue. Just check. So this is kind of 4.3. There are a couple of theorems we talk about it. Then we look for some of the nice spanning sets, which is going to be linearly independent, and it creates the space for us. So that's going to be called a basis. So that's the target for 4.4. That is where probably we'll get up to the 4 or 5. Let's say 4. for the next week. Okay, so the target is you should be able to do up to the 4.3 this week. Okay, so have a good one. I post this one and then I will finish it, just a couple of theorems, by Sunday or Monday and give you another one. Okay, so any question, just email me, let me know. Just keep up, read these sections. As I told you, notion of the vector space is very important. Go through the problems in your book and quickly get the problem on the practice quiz that I'm going to post for you. I will give you the solution later, but I post it for a couple of days so that you get an idea. Then I give you the solution of practice quiz number 2. Okay, take care and have a good day. A good day, good, nice weekend. That's it. Bye-bye.